Hi, my name is Vivekanand and I'm a part of the Ashton Graviel Spatial Orientation Lab at Brandeis University. Now imagine that you are an astronaut on your way to Mars and you spend months and months in zero G, and then comes a day when you have to land upon the surface of Mars, and in doing so you have to experience a gravitational transition from zero G to Mars G. And during that initial descent, you will not have reliable gravitational cues. On top of that, even as you approach the surface of Mars or the Moon, because they're smaller, the gravitational cues will be very different than what you're used to. And then even on top of that, there will be multiple stressors, both psychological and physiological. And what we know is that all of these factors will make it so that astronauts will become very susceptible to spatial disorientation. And all that means is they'll lose sense of where they are relative to upright, something which you really need to know as you're trying to stabilize a spacecraft and land it upon the surface. Now, some people might say that, look, by the time we get to Mars, the process of landing will be automated. But technology can fail. And not only that, forget Mars or the Moon. Here on Earth, where we have a very good sense of the terrain, the weather, you can talk to HQ immediately. In military pilots, spatial disorientation is a leading cause of fatal aircraft accidents, right? This is where people are dying. And not only that, 90 to 100% of pilots will experience spatial disorientation in their lives. So this is a huge unsolved problem. So now the question is, how do we study it? How do we recreate a spaceflight analog condition where people cannot rely on gravitational information here on Earth? And the way that I do it is I strap people into this machine. Now first I'll describe the control condition, and then I'll describe the spaceflight condition. So this condition, the control condition, I also call it the upright condition. I strap people into it and it's programmed to behave like an inverted pendulum. And humans are given the task to grasp that joystick and stabilize it to the best of their ability at that 0 degree point right at gravitational vertical. Now, if you're interested in just the control condition, I've published on it, so check it out. In terms of sensory information, because people are blindfolded, they cannot use visual information. Because they wear noise-canceling headsets, they cannot use auditory information. Really, the main pieces of information that they're receiving is vestibular, and to a secondary extent, the touch receptors on their skin as they push against that machine. Now, the vestibular system, we can take a magic school bus ride to investigate it, resides in your inner ear and has two parts. The first are the semicircular canals, and these detect angular acceleration during rotations. Then the second part are your otolith organs, and these are fine little hairs suspended in gelatinous material adorned by crystals, and they detect linear acceleration. And really, for today's presentation, they detect tilt from gravitational vertical. The more you tilt from gravitational vertical, because gravity is pulling on those crystals, the more those hairs will deflect, telling you where upright is. So to summarize, in this upright control condition, even though I'm blindfolded, I have a pretty good sense of where I am because my otolith organs are telling me the balance point is here. The further I get away from the balance point, the more those hairs deflect, so I can use gravity to figure out where that balance point is and where I am. Now, my second condition, I take people, I put them on their back. I call this the spaceflight analog condition. All the dynamics are the same. Same inverted pendulum dynamics, same task of trying to stabilize around that 0 degree point. Well, why is this a spaceflight condition? Well, if you remember, in the upright, the further away I got from the balance point, the more those hairs deflected. I could use gravitational cues to figure out where I am. But on your back, you're always the same distance from gravitational vertical. So whether you're at the 0 degree point or you're really far away, it doesn't matter. Those otolith hairs are just saying you're on your back, you're on your back, you're on your back. You cannot use gravity or gravitational cues to figure out how far away you are from that balance point. And because there are no reliable gravitational cues for the task, it's very similar to what astronauts may experience, especially during that initial descent. Now, I've published heavily on the difference between upright and the spaceflight condition, and I've presented on it before. I'm just going to give you a very quick summary. In the upright, where people know where they are because they can use gravitational cues, they show very fast and robust learning. Whereas in the spaceflight condition, where they do not have relevant gravitational cues, collectively there's very minimal learning, collectively there's very poor performance, and very high rates of crashing. And again, just so you emotionally feel how surreal this situation is, 90% of participants say, I don't know where I am, I'm disoriented. 100% of them show it in their data as a characteristic pattern of positional drifting. And 10% report unusual illusions. Some of them will say they feel like they're completely upside down even though they're on their backs. Now here are the papers. If you're interested, check it out or just contact me. I'd love to talk about it. Now, I was very curious about individual performance in the spaceflight condition. Are there people who actually do well? So to investigate that, we used machine learning to cluster people into groups, and we found that the proficient group participants actually showed learning across majority of the metrics that I have. I've got like 20 metrics. And then there were the not proficient group participants. They actually became worse as time went by. As they had more practice, they actually got worse across majority of the metrics. And they all, interestingly enough, converged at the same suboptimal strategy. And if you're interested in the machine learning and the suboptimal strategy that they converged at, check out this paper over here. Now, just to give you a taste of the night and day difference between the proficient and not proficient group people, the top panel is the proficient group. And this is just raw data. Look at that red line. It's just what they're doing with the joystick over time. You can see small magnitude deflections, and there's a lot of variation to it. Now look at someone in the not proficient group. These people take the joystick and they smash it as hard as they possibly can. And this causes the machine to do wild oscillations. And you may not be able to tell here, but they hit the crash boundary 3 times in just 30 seconds. That's how out of control they are. Now, I am sitting and almost having a mild heart attack watching this happen in front of me, wondering why do the not proficient group participants display this kind of behavior? And one idea I came up with was maybe biologically, their vestibular sensors, maybe they're just not accurate. Maybe they just don't have a good sense of where they are in space, and therefore they can't do the task. And so really the hypothesis I came up with is people in the not proficient group have poor spatial acuity, don't know where they are, and therefore they're not being able to do the task that well. That's the hypothesis. How to test it? Well, I brought back participants who had already done active balancing in the spaceflight condition. I put them in the upright and also on the back in the spaceflight condition. And then I told them, you're not going to control the machine anymore, okay? You're just going to sit there blindfolded and experience passive pre-programmed profiles. And these profiles, had them cross the 0 degree point multiple times. And their only task was to press the trigger button and indicate whenever they felt like they passed the 0 degree point, whenever they're at it. And we measured spatial acuity, their sense of where they are, by how accurately they were able to trigger press that 0 degree point. Now, surprisingly, just mind-blowingly surprisingly, there was no correlation between a person's spatial acuity, how well they knew where they were, and how well they were able to perform in the active balancing task. And this blew my mind. I was just not expecting that. Why? Okay, so I looked at the raw data, okay, and just to orient you here, this is a representative participant. This is in the upright where they have a very good sense of where they are. The blue line is their angular position. Okay, and what they have to do, and again, they don't have control, they're just going through this passive movement, they just have to trigger press, and that faint black line around the 0, that is the 0 degree point. So you can see this person, these diamonds are the trigger presses, does a great job of indicating whenever they are at or near the 0 degree point. You put the same person on the back, and I don't even know what's going on. Okay, at first, they're quite accurate, but within 10 seconds, just 10 seconds, this person's at 50 degrees feeling as if they're at 0 degrees. And the truly bizarre thing is after 40 seconds they stop trigger pressing. And you ask this participant and the other participants that display similar behavior, in fact, yours truly shows similar behavior. After this 40 seconds, the participant said, oh, I never felt like I was ever back at 0 degrees. But in fact, they really were several times back at 0 degrees. So it's very unusual. Some people report feeling like they're 180 degrees away when really they're at 0 degrees. Very unusual. Now you look at participant B, who is also a representative participant, does wonderfully in the upright. You put them on the back where they do not have gravitational cues, and they're trigger happy, like a little machine gun. They just light this up like a Christmas tree everywhere. They could be far away or close by. They feel like they're at the 0 degree point. Very unusual. Now the first general conclusion I want to make is that, in my opinion, a general countermeasure for spatial disorientation, like a warning signal, I don't think it's going to work. Because if a warning goes off and participant A thinks they're 180 degrees away and participant B thinks they're only 10 degrees away, their actions are going to be radically different. And so in my opinion, we need to have a customized and personalized countermeasure for every individual's unique perceptual profile. But before we can do that, we need a lot more research in characterizing individual differences in their perception, which is really, there's not a lot been done on that. The other general conclusion is that spatial acuity, which includes vestibular thresholds and path integration, that alone is not sufficient to predict performance in our disorienting spaceflight condition. And this is kind of cool because it means you can't just say, sorry astronaut, you can't join because your vestibular accuracy is not that great. It means that most likely through learning and training, people are compensating for their weaknesses. And if you're interested in this sort of thoughts, please check out this paper over here. Now, the next question I had was, could susceptibility to vestibular stimulation be the key? And there is literature that suggests that vestibular stimulation can lead to performance decrements. And what we did is we strapped people into this machine over here and rotated them in earth vertical yaw as they made head movements in pitch. And this has been shown to be a provocative vestibular stimulation. And unfortunately, I don't have time to go over the complexities of this. I'm just going to give you a teaser. And if you're interested, check out this paper, which has just recently been published. What we found is that those people whose spatial acuity worsened as a result of vestibular stimulation, they were the ones who actually performed poorly in active balancing. But the correlations were only significant for the first few trials of early balancing. You might be like, why? Well, it kind of makes sense, because in the early trials, when you first get into this disorienting condition, people are panicking, they don't know what's going on, they're smashing the joystick, even the good ones are doing that, and they're experiencing these high velocity movements, very large amounts of vestibular stimulation. So it makes sense people who are not able to deal with vestibular stimulation would be the ones who perform poorly. In the paper, we talk about how this may be related to attentional demands, and we also talk about how vestibular thresholds, path integration, motion sickness susceptibility, and mental fatigue are not the prime reasons why this correlation was significant. And if you're interested in that, just check out the paper. What was also interesting is that we didn't find correlations with late trials in active balancing. And what this again suggests is that participants were able to compensate for their limitations in their vestibular system through training, through learning. And so training really does matter. Another concluding idea is that this type of vestibular stimulation may actually be a valuable way to assess individual differences in that initial exposure to a disorienting condition and tailor a sort of training program particularly for them. And so if you're interested in all of this, this is the new paper, check it out. Okay, I would love to collaborate, love to talk to anyone, so definitely reach out. The 4 major research thrusts I have is human augmentation, and my next project is on vibrotactile feedback as a countermeasure. I'm exploring AI, machine and deep learning as countermeasures, of course, basic science of spatial disorientation, and I'm a former high school teacher, so educational outreach is very important to me. There's going to be a poster session where Yonglin will talk about the work that she's done using deep learning and predicting when people lose control and crash in this paradigm. So check that out, and also we have a paper coming out on that topic, so you can read about it there. A great thanks to Trish for the Go4Me launch and everything, for the funding. Thank you so much. And any questions, and definitely reach out.